In this video, I am going to show you how we are able to calculate the A and B parameters of van der Waals equation of state using the critical point. So we're able to do this because, as you can see at the critical point, the derivative of the equation will be 0. The derivative, or the second derivative, will also be 0. So I know this because the equation changes from concave up to concave down at that point, and it's also a flat point in the graph. So because it changes from concave up to concave down, I know the second derivative is 0. Because it is a flat point or a peak, the first derivative also has to be 0. So those will be our two equations we use, and we'll also, since the critical pressure, temperature, and specific volume will be known because that's something you can measure in a lab, we'll be able to use those to calculate B and A. And I'll show you how to do that in the next part. Alright, so as I said, the derivative of the van der Waals equation with respect to volume at the critical temperature and critical volume will be 0, and the second derivative will also be 0 because it is an inflection point, and the first derivative is 0 there. So we're actually going to calculate the first derivative and the second derivative and use those to find expressions for A and B at the critical point of a substance. So we're going to take the first derivative. So this will be R times T in the numerator, R times temperature, times B minus B squared multiplied by -1, and then the derivative of the second term will be positive 2A over the volume cubed. And so since this is at the critical point, it'll be the critical temperature and the critical volume, right? And it is 0 at that point. So now I'm going to take the derivative again to get the second derivative. So this will be, it will now be a 2R times TC over BC minus B cubed minus 6 times A over B C to the 4th. So here's our second derivative, and it's also 0 at the critical point. So now we're going to use these two equations to calculate our two unknowns. So I'm going to switch colors and kind of rewrite these equations. I'll rewrite them up here. So now we'll have R TC critical temperature over critical volume minus B, critical volume minus B squared will be equal to 2A over the critical volume cubed. And then rewriting the second derivative, we'll have 2 times R times the critical temperature over critical volume minus B cubed equals 6 times A over critical volume to the 4th power. So now I'm going to take the reciprocal of this equation and multiply it by this equation to kind of simplify it down, and that'll give us one equation that lets us solve for B. So we will get V, the critical volume, minus B over 2 equals, this will give us critical volume over 3. 6 over 2 is 3. Alright, from here, we can go ahead and continue and solve for V. So we have critical volume times 2 will be 3 times the critical volume minus 3 times B, and that means B is equal to the critical volume over 3. There's our expression for B. Now I'm going to go ahead and plug it back into this equation up here and use it to solve for A. So I'll just keep moving this way. Kind of awkward, but we'll keep going with it. So we'll have R times the critical temperature over critical volume minus B, we'll plug that in. So it will be VC over 3 squared equals 2A over the critical volume cubed. This will become 2/3 times the critical volume. When we square it, it will become 4 over 9 times the critical volume squared. So it'll be 9 over 4 times R times the critical temperature over the critical volume squared equals 2 times A over critical volume cubed. Now from here we can go ahead and solve for A. So we'll get 8A times the critical volume squared equals 9V critical volume cubed times gas constant R times the temperature, and we will just divide by 8 times the critical volume squared, and that will give us A. So A is equal to 9 over 8 times critical volume times R times C. I'll write this. We'll rewrite this a little bigger. We'll write it over here. So A equals 9 over 8 times the critical volume times R times the critical temperature. So here is our expressions for B and A. Alright, so now I'm going to use our expressions that we found for B and A to solve for the critical compressibility. So the compressibility factor is Z, and it's defined as the pressure times the volume over pressure times the specific volume times R times the temperature. So for an ideal gas, this value is 0, but we're not working with the ideal gas equation anymore. So I'm going to go ahead and calculate the value for Z at the critical point. So we're going to start by plugging B and A into this equation. So our critical pressure, since we're at the critical point, equals R times the critical temperature over, plugging B in, we'll have 2 over 3 times the critical volume minus, we'll plug A in now, so that's 9 over 8 times R times the critical temperature times the critical volume over the critical volume squared. So this will cancel out with one of these. I'll go ahead and rewrite this. This will be 3 R times the critical temperature over 2 times the critical volume minus 9 times R times the critical temperature over 8 times the critical volume. So now that we have this equation, we can factor out R times the critical temperature over the volume. So I'm going to go ahead and factor that out down here. So we'll have the pressure equals, factor out R times temperature times critical volume, and we're left with 3 over 2 minus 9 over 8. So getting a common denominator here is 8, so this becomes 8, and this will be 12/8. So 12/8 minus 9/8 will be this times 3 over 8. So now we can divide the left side of our equation by the right side, and so we'll have pressure times volume over R times critical temperature, which, if you see, this is Z, so this equals Z, which equals 3/8. So this means that for any pure substance, the critical compressibility factor is 3/8.